So there's a general rule that organizers should not speak at the workshop they organize. Of course, I want to respect this, but my estimated co-organizers insisted that I have to say something. So sorry. Well, I try to give some historic review, what ideas Harald and I had over the time. So it's not really a research presentation. Good. So as many of you, I start looking back. 25 years ago, a little bit more, I was postdoc in Marseille, and then was time to think about continuing. I thought about Marie Curie, and clearly, okay, this needs some host. And it was absolutely clear that the ideal host would be Harald, because, well, I had some work with Thomas, mentioned later, on quantum fields along with spaces, and Harald did this many years before, especially with John Mador, Peter Preschneider, and others. And so the plan was to more in spirit of quantum physics, and Harald was clearly, you could imagine. So I wrote an email, and Harald replied, and he invited me to the Schrödinger Institute in April 99. And we discussed this project. We submitted in May, and and well, okay. So then, well, we got it, and was a starting point of a really wonderful and extremely harmonic collaboration. Quite successful. So I counted this morning. I counted 51 joint papers, plus some few more Wolfach abstracts. Okay, well, that's something. And yeah, thanks a lot for all this time. So I'm not afraid of long calculations, and I can do this, but the danger is that I run into a direction where I'm completely lost. And Harald always kept the overview. And so he understood things which belong together, and he brought this input from many other interactions with colleagues and with talks, and this really shaped right, so I'm in a happy situation that Richard explained this extremely well, the starting point, which came then from the written paper extending Volker. So I can be short here. Right, so this came before submitting this Marie Curie proposal and then really starting, and it changed everything. So the work which we wanted to do never happened. So we started here. Right. So yeah, okay. With Thomas, we had this work on one loop realization of the effect Mills on the torus, and we understood that in one loop order everything's all right, and we tried to think about higher order, and we didn't manage quite. And then came this, as Richard explained, this time surprising observation that it does not work for reasons which Richard explained. So this is then so Minweiler von Rahmström-Seiberg, they called this UV-IR mixing. Okay, so this you have seen from Richard. There's representation of the Moyal product. There are these phase factors, and in planar graphs they perfectly cancel. All right, nothing changes except for certain two factors, and in non-planar graphs they are there. They make the graphs convergent, but so they noticed Rahmström-Seiberg that they create then well, because okay, in one of these Qs, say, is an internal loop momenta. Okay, then it's regularized by the P, but if P goes to 0, then the phase is no longer there, and okay, there's this problem. Okay, this was explained. So I should emphasize that there were really impressive articles by Jeffrey Roybahn, who proved that this is completely robust. So it's not only an effect in this special situation, so it's really there. All right, yeah, and then so in this situation, I came to Vienna and we tried something also with Thomas again, but was limited. Good. So then something happened, something important, namely Harald was contacted by Manfred Schweder from Technical University. And Manfred always had many young students. And there was one group around Andreas Bichel, Jesper Grimstrup, Lukas Popp. They were assigned topic non-conflict theory. And since Manfred Schweder knew that Harald is the expert, so he contacted Harald, and then Manfred suggested to do it together. And this was quite successful. So there were some meetings, I don't know, where these young people came into contact with other young people from the group of Julius Wess. And this group studied the Seiberg-Witten map. And so our idea was then that we should study loop corrections. So take the Seiberg-Witten map as input for confit theory, study loop corrections. So I should say Harald got a very prestigious Leibniz professorship in Leipzig. And so he was not there at this time, participated remotely. So in some sense, our joint collaboration started when I was away again. So it started after my stay in Vienna because Harald was in Leipzig. So anyway, this worked quite well, at least for some time, but in the end we understood this will not work in general. So then I went to Leipzig, Harald back to Vienna. Okay, and then somehow maybe we both did not want to accept that this UVIR is a problem that there must be a waiver. So, okay, and then there were two important input, one by Thomas again, who convinced me that the approach of Polchinski by exact renormalization group equations is the right thing to do renormalization in confit theory. Okay, thanks. So, okay, this I want to try, but you see, maybe I'll go back here. So with these phase vectors which make everything convergent, there is no chance to run the Polchinski machinery. So you need really somewhere absolute convergence and things like this. So this will not work. Okay, and but was also a meeting here at the Schroeder Institute where Harald and I and also José Garcia Bonilla were here. And José told us, well, these Moyal algebras, they are isomorphic to infinite matrices, and this isomorphism is really explicit. It's given by Laguerre polynomials. So we translated everything in this matrix setting with Laguerre polynomials, and then, well, we tried to run Polchinski. So Polchinski's induction proof, you need to know the result which you want to prove. Okay, means we have then input some certain scaling behavior, and then you prove that, well, it works by induction. And what you need for this is because the disadvantage with the matrices is that the Laplacian is no longer diagonal. So it's a complicated matrix, and you have to invert it. So this becomes tricky, and we need bounds for how the matrix, the inverse, falls off if you send the matrix indices to infinity. Okay, so, and well, inversion, well, I did numerically for whatever, and then I saw this does not work. So we saw also in this matrix formulation this UVIR problem. It did not work. Okay, so, well, here is the beginning of a letter, email. I wrote to Harald somewhere in November 2002, where suddenly it worked again. So not all of you will understand German, but those who know, okay. Somehow this UVIR problem, I saw in this matrix business as the need to have position-dependent mass renormalizations. Really strange. So, and then somehow I saw if we arrange them in a very special way, such that this position dependence is that of a magnetic field. Okay, it's the simplest thing, but imagine. Then I run again my computer program, and then suddenly this inverse of this covariance had the right decay properties. So in fact, it was not exactly, okay, looking closer, what exactly magnetic field, it was this harmonic oscillator potential. Okay, anyway, so this was then, after some time, the proposal. And I should say, it was also mentioned by Richard. We saw shortly later that there is a deep reason for having this term, namely the duality of Edwin and Richard, which leaves here this interaction invariant, but it exchanges these two. It changes the usual kinetic terms and the oscillator terms, because in its duality between direct and momentum space, and the Fourier transform is then p square, and p is converted to x, and so they are exchanged. So, and the quantum theory wants to respect this duality. So, if you have this term present because it's divergent, you must have also the other one. No chance. So, and then I should say that Edwin Richard and with Constance Sarembo, I don't know whether we had some exchange. And so they took this magnetic field more serious than we did, and they managed to convert it into a complex matrix model, I think even a very general potential, and they managed, impressive result, to prove that this is exactly solvable. So, okay, I should say omega here is quite general, and later it was a great idea by the French group, set omega equal to 1. Then we come very, very close to such a matrix formulation. And but there are differences, and I tell you them on the second to last slide. So anyway, so there's one remark, and the second is that Harald and Harold, they had the great idea to look at phi cube in the setting. They understood that with input from the conservative model, but with understanding what renormalization means, they can manage the phi cube model in dimension 2, 4, and eventually 6. And so it's far more than conservative model. It needs to understand what renormalization means, and they had this result. And much later with Akifumi Sako, and then we came back to this. All right, so that's the situation. Good, okay. Now, we had this term, then we knew more or less the decay properties, had conjectures about scaling laws, so we finished all this combinatorics and this induction proof. Good, and then this was first relatively easy to get phi to the 4 in 2 dimensions in 2003. So I have to stress that this has no chance to work in 4 dimensions. So the reason is the following, because with the scaling laws, you just prove that, for instance, the 4-point function, planar 4-point function is divergent. But there are infinitely many of them. They have different matrix indices, and you just prove all of them that are divergent, and then you need, again, infinitely many parameters. So the challenge was to prove that the difference of 2 2-point functions actually converges. So that only you have one reference function, which you renormalize, and all other differences, they are just finite. And with the information which we had no chance to do it. And then again, the Schrödinger Institute rescued us. So Harald was somewhere here in a talk, what event, where Jacobi matrices appear. So not Jacobi in sense of Jacobian of transformation or whatever, but three-diagonal matrices with certain properties. And Harald saw immediately, well, this is what we need. And then I came later and we sat at this long corridor at the computer and we played around with orthogonal polynomials. So the Malcolm polynomials were the one which worked. So we understood how to exactly invert our string operator, the covariance in terms of Malcolm polynomials. Good. So, and then with this exact result, was straightforward to prove that the difference of four-point functions always converges. One alone is divergent, but the difference is finite. This was okay. So now something else important. So, well, Pochinski is renormalization group language. And in this language, you have relevant terms, marginal and irrelevant you can ignore. Relevant is the mass, and we have three marginal terms, namely the wave function renormalization, coupling constant, and the oscillator frequency. So now with our exact formulae, we were able to compute exactly this one loop renormalization group flow. And really unexpected result was that this ratio, coupling constant divided by square of the oscillator frequency, stays constant over the whole flow. Also we knew that omega runs to this Edwin Richard self-dual fixed point omega equal to 1. Consequently, the coupling constant stays bounded in the ultraviolet. So the same mechanism which cures UV-IR also tames this unfamous Landau ghost. It was completely unexpected and not intended. It just came out. So, and this, we had exchange with Vincent Grosse, who became very excited. So this was something he was searching for decades. Vincent and his large group, they brought very important input into this game. So they made a very drastic but enormously influential observation. Well, let's set omega to the RG fixed point, omega to 1. And then they managed, so with Margarita Di to compute the three loop order, and they saw, well, this is much easier than what we did, but three loop is then harder. They saw that the coupling constant has no infinite renormalization at three loop order. And then it's clear there must be something around, and they found it. As far as I know, they had some input in discussing with Miri Mastropietro. We also tried to invite him, but he had at the same time something in Rome, I think. So they found what they call the Ward identity, which then, so it's a new symmetry. With this symmetry, they managed to prove that the divergent part of the four-point function comes alone from the divergent wave function renormalization. There is no proper flow, no proper infinite flow of the coupling constant itself. The four-point function is divergent, but the entire contribution comes from the wave function renormalization, which was so okay. Somehow I saw this preprint, I told Harald, and then Harald said immediately, now we have to solve the model. Because apparently he knew that, okay, that's the key. And of course, Harald was right. Okay, at this time I got my, okay, thanks to all this work with Harald, I got this job in Münster, and my first sabbatical was in 2009. I came here to the Schrödinger Institute. Anyway, so I was a long time here in Vienna. In this time, we really brought this idea to an end. And so we obtained a very complicated nonlinear equation for the renormalized two-point function alone. Well, it's a Dyson-Schwinger techniques, and usually there's an infinite tower, and you can't do much. But here, thanks to this word entity, we obtain a closed equation. Well, later we understood it's not the best. Okay, the communication is horrible. And I show here the unrenormalized equation. So this part M, the mass, diverges, also Z diverges or goes to zero, whatever. So we have to keep a cutoff, but the cutoff equation looks simpler. Okay. And we already, was also some idea, it's better to write an integral equation. Of course, you can suppose this measure is the sum of Dirac measures, and then it's back in the old formulation. But connecting it to continuous function allows then complex analysis tools. Here, Hilbert transform is something which we understood in the following years. Okay, the first formula was, or the proof was graphically similar as by Grosse and collaborators. And then we had it more analytically. And then we extended enormously. So we had exact equations for all possible correlation functions, any genus, so this is grading. And also we proved that, also Harald's idea, going around Brunnen, whatever, that certain of them are just algebraic. There are no integral equations, whatever. You can write down an algebraic recursion. Not for the two-point function, but for others. Okay, and then thanks to this Hilbert transform representation, we were able to reduce everything to, because this was original function of two variables, now we can set 1 to 0 and obtain a nonlinear equation for an ordinal function of one variable. And by fixed point theorems, we proved existence. So, okay, more or less this was then done. And then my second sabbatical. 4 years later, we had here a very fruitful interaction with Gandalf. And there in this time, we translated these formulae to position space. And we saw, well, this is, okay, to restrict to this planar sector, we have to make theta, this deformation large, ideally infinite. And in this limit of infinite noncommutativity, this oscillator term goes away. So we restore translation invariance in this limit. So it makes sense to translate everything back to position space. And then the question was, do we get possibly reflection positivity? So this was what we did. And but somehow it did not work. It was not possible to get precise enough information about this solution of our equation. So somehow it tried hard, but it did. So something what really changed was then. So I always looked into 4 dimension. 2 dimension I somehow never really considered. It turned out 2 dimension, as you know, is simpler. And strangely, together with Erik Panzer, I was able to solve this equation. In the 2-dimension case, 2-dimension means this measure is just, so it's t in 4 dimension, and it's 1 in 2 dimension. That's the only difference. And then this equation is still nonlinear. We were able to solve exactly in terms of the Lambert functions from the 18th century. Here. Sorry. Okay, so we had the exact solution. And then around the same time with my students, we solved here this algebraic recursion. It's a beautiful combinatorial structure in terms of something which we called nested Catalan tables. Some integer sequences which count them, so iteration of Catalan structures. Okay, and then, so my student, Alex Hock, visited Akifumi in Tokyo, and when he came back, he said, did you notice this relation? So with Eric, there is some intermediate formula where it's of this form minus f plus log of negative f, and f as roughly is the inverse of exactly the same equation. Okay. Of course, I didn't notice this, but I understood. It was completely clear for me what one has to do to solve the equations generally. So here, that's the recipe. Okay, so two-point function. So this is something which we knew before in 2012. It's possible to represent it as a Hilbert transform of some angle function. And so this angle function is the argument of the complex logarithm. So it brings some I here. And this is the key ansatz. I is negative R of negative R inverse. Mass is not important. So this is the translation of that. So what is R? So somehow it's a sort of status transform, but the measure is, so here is rho naught. Of course, I thought, well, this should be rho naught, but it's not. It's rho naught only in 2 dimensions. So let's put some general measure. And then go into the equation, and surprisingly, this linear equation is identically satisfied if we set rho naught of RD is rho lambda. So it's again a complicated system, but then this linear equation is identically true. Good, so then there was a workshop organized by Kasha in York, where we present this, and there was still this one trouble with 4-dimensional case. Namely, so here's the equation in 4 dimensions. It's then some taking limit. It's a Fredholm equation, and it seemed that, well, rho lambda is same as rho naught, is t, and then you see, well, this, well, to make this roughly, you need 1 epsilon roughly to make, if this is t, you need some, okay, one that you can kill, but not everything. And then you guess somehow that the second term, because the negative sign is larger, and then as a function, this R4 will develop a maximum, and then will go down to negative infinity for that large, and therefore you get the cutoff because this inverse does not exist beyond the cutoff, and this exactly the same triviality problem which we had. But things were nice, and so we combined by different methods. Harald identified differential equations satisfied by this function. Alex tried resummation, so really you solve Fredholm equations perturbatively and then resum. And we found there is an exact solution given in terms of the hypergeometric function. And now the important thing is very interesting. There's a dependence of the parameters as a function of the arcsine of the coupling constant. If you expand it, it's a horrible function in terms of hyperlogarithms. Exact solution. And now essentially this, so before we had rho naught of z is z, and so this asymptotics describes the spectral dimension, and the spectral dimension of this function is reduced to 4 minus 2 pi arcsine lambda over pi. It means the planar theory lives effectively not in dimension 4, but in a reduced effective dimension. Therefore, the triviality goes away. It's only possible to see it. No chance in perturbation theory. It's only the exact solution. Okay, yeah, I think it's okay. So, okay, now final part. Topological recursion. Some of you probably heard it. It's a great discovery around 2007 by Nicolas Antin and Bertrand Hénard. They observed that many matrix models have a common structure, which they call topological recursion. So we need some ramified covering of Riemann surfaces and so-called kernel. And from just this data, one builds a family of differentials, and they describe correlation functional matrix models. So we know today that this model, which Edwin, Richard, and Raimar had, this satisfies topology recursion. The Kontsevich model also with randomization. So everything satisfies topology recursion, and many, many more. And also is observed in very, very different areas of mathematics. Okay, so with my students, I found the correct definition of the omega gn in our quartic real case. So it's relatively complicated. You start from two variants of two-point functions. Sorry, here is something missing. This typo. Here I have to insert phi AA and phi BB. Anyway, there are two-point functions. They play a different role, and then from them, so they are functions of here this external matrix, but this also appears in the Z. To make it measure. So it depends on a complicated way on these eigenvalues of the external matrix. This finds these omegas, and then there's a way to extend it. And to our surprise, it does not satisfy topology recursion, but an extension called blocked topology recursion. So this makes everything more complicated. In principle, everything is computable. And from these omega GNs, everything is found. So roughly, maybe I can here. So this term is one of the omegas. So if we can compute them by other methods, then everything else is just linear. And so there's structure behind these terms. They satisfy the recursion, and then everything is solvable. All right, so now to conclude. So everything is true, what I said about topology recursion for the matrix model. But our topic is 4 dimensions. And then all this nice structure on blocked or whatever topology recursion breaks down. The reason is that there's a sum over ramification points and limit there are infinitely many them, or they collide or form branch cuts. So it's a horrible situation. Our spectral curve is given here by the hypergeometric function, so it's no longer algebraic. So this has no chance to work. So we need something else. And what exactly, I don't know, but my feeling is, well, we have to do analytically work, and maybe one should take advantage of these great developments in stochastic analysis over the last decade to view our planar sector as an equilibrium limit of some stochastic process. So the idea is throw away everything which is non-planar, just look at the planar sector which we understand completely. Or maybe this is this Breit confit theory which Richard presented, so something like this. So that this planar sector should be understood as a quantum field theory in its own right. Understand as a stochastic process, get the stochastic PDE of it, and then use these methods because we are in a subcritical regime. So our dimension is not 4, we are in 4 minus epsilon. Epsilon is concrete. So therefore, these methods should work, and the hope is that in some future, so I learned from Akifumi, 88 is the next big step. We can report something. Okay, thanks a lot, Harald, for all this, and happy birthday.